So welcome back. We are going to talk about a new topic today. Again, like we always do, this class is only about giving you a bit of a help. Okay, the main content delivery or the lectures is going to be through Professor Tetro's material, right? So he posted the material online, and most of the learning is going to be through his videos. Okay, here I'm just going to give you some practical hints, tips that you can use while solving problems or understanding concepts. Okay, so in that process, let me see if I can go here and take a quick look at the syllabus, wherever that is. Okay, syllabus. I swear I have seen it right here. Okay, so we are in week 5. We are in week 5, meaning that we should start with frequency selective circuits, chapter 14. Okay, you should have completed Bode plots by now. So with that understanding, with the idea that you must have finished Bode plots, I'm going to give you some hints, easy tips, very, very straightforward techniques to remember Bode plots. Okay, let's assume you have some transfer function in this form, K naught. Okay, I don't know, S or 1 in the standard form, 1 plus S by Z1, right? 1 plus S by P1, 1 plus S by P2, 1 plus S by P3, something like that. Let's do just 2. Okay, poles. So this transfer function, if you write it in the standard form, any transfer function, the roots of the numerator, as you know very well, are called zeros. Okay, so P1 and P2 are called the poles. Right? P1 and P2 are called the poles. So how do you write the Bode? How do you do the Bode plot? When you're given a transfer function that has been written in the standard form. Okay, once it is in the standard form, there are certain rules that we can more or less use to, in a very simple manner, okay, in a simple manner, derive the Bode plot. Okay, I'll give you certain rules of thumb. First of all, okay, any pole contributes 90 degrees phase shift. Okay, and that's it, not more. Any pole can only give 90 degrees, negative 90 degrees of phase shift. Okay, zero, on the other hand, that guy contributes a pole phase shift raise of 90 degrees. Okay, a phase shift raise of 90 degrees. Okay, when you're drawing the Bode plot, okay, even for homework problems, okay, if you're able to understand this method, you may actually be able to get away without doing the calculations. Okay, so the first thing you do is that plot the location, identify the location of zeros and poles. Okay, let's say there is a Z1 over here, there's a P1 over here, and there's a P2 over there, poles. Okay, everybody understand that there is a 0. Okay, there's a pole 1 and pole 2. Let's separate them a bit for our initial discussion. Okay, so when you're plotting on a log scale, this is a logarithmic scale, the x-axis, and the y-axis is 20 log of the transfer function gain. Okay. This is V out over V in, right? V out over S, V over V in of S. That's the transfer function. Okay. So when you're looking at the zero, what a zero does is, of course, you do have to take into account the magnitude of this guy. 20 log K naught is the DC value. Whatever that value is, 20 log K naught, whatever that value is. So you're starting off of that type. Okay. So when you're plotting your magnitude response, okay, a zero always raises, okay, and it continues to raise the magnitude at a 20 dB per decade. Okay, so when you hit the zero frequency, your magnitude begins to increase at 20 dB per decade. Okay, and then you continue along the y-axis with that. Okay, and when you reach this pole frequency, which is this guy, okay, when you reach this, the pole always has a property of bringing down. Okay, bringing down. So because of pole 1, you expect a negative 20 dB per decade effect. Okay, when you hit the second pole, for example, then there's going to be a further drop of negative 20 dB. Okay, negative 20 dB. A further drop of negative 20 dB. Okay, so there are a bunch of different factors changing your magnitude. There is a constant, okay, that's this guy. That's a DC gain. We sometimes call it as a DC gain. Okay, so when you're looking at the pole response in this region, okay, once you start hitting P1 and before you actually reach P2, there are two forces acting. There is one force that is Z that is trying to increase, and the other guy, which is a pole, that's trying to decrease. Okay, so in between these two regions, there is an increment because of zero, and there's a decrement because of the pole. So what happens is, in this region, the net effect is going to be that that the magnitude response is going to be flat. Okay, but then you begin to hit the, you begin to notice the effect of the second pole, which is to drop the magnitude response by 20 dB per decade. Everybody with me? So the idea with magnitude response or the pole and the zero behavior or effect on magnitude is that it continues indefinitely. It does not end. So in other words, this effect continues as long as you continue to increase the frequency, the magnitude continues to drop. Okay, questions please, questions so far? Everybody with me? So the simple idea is a zero increases your gain by 20 dB per decade. A pole rolls your gain off by 20 dB per decade. Okay, and then depending on the relative location here, all the poles are separated enough. Okay. On the other hand, if this pole were sitting right on top of the first pole, then you would see a negative 20 dB per decade roll off, plus another 20 dB per decade. So the roll off is going to be much steeper. Okay. Everybody with me? The roll off is going to be much steeper. If this zero were not present and then the poles were sitting right on top of each other. Okay. So very straightforward to see. If you have two poles sitting here, pole 1 and pole 2, in the absence of zero, the magnitude response does not change at all until it hits the pole frequency. Then it begins to roll off at negative 40 dB per decade. Because there are two poles, each contributing a negative 20 dB per decade. Okay, so in effect, the overall roll off is going to be much steeper, negative 40 dB per decade. Okay, so that's about the magnitude response. When it comes to the phase response, okay, and there's a reason why I separated these pole 1, pole 2 with enough gap here. Let's say this is a log scale, right? So let's call this 10 times Z1 by 10. Okay, a tenth of zero, and this frequency 10 times zero. Okay, similarly, when you're looking at the pole frequency, these numbers become important. Okay, a tenth P1, 10 times P1. Similarly, the same thing here as well. Let's use this color. Tenth of P2 and 10 times of P2. Okay, so wherever the phase begins, okay, wherever the phase begins, if it's beginning at zero, then let's say here is my okay, if the phase begins at 0 degrees, okay, what a zero does is, if this were your zero location, okay, a zero contributes 90 degrees to the phase shift. Okay, the way it works is at a frequency 10 times below Z1 and 10 times above Z1, this is where the complete phase shift from zero comes in. So some going to be like this. Okay, the effect of Z1 begins at Z1 over 10 and ends at 10 times Z1. And this increment is 45 degrees per decade. Okay, meaning that if the frequency is going up tenfold, the phase shift is going to be 45 degrees. Okay, so at Z1, there's going to be an increment of 45 degrees to the original phase. Okay, and when the Z has completed its effect at 10 times Z1, if you look at the phase, that's going to be a gain of 90 degrees of phase. Okay, and then nothing happens until you hit this next important frequency, okay, which is 10 times pole 1. What a pole does is it contributes a negative 90 degrees phase shift, right? So between a tenth of the pole value and 10 times the pole value, okay, there's going to be a 90 degree roll off. So it's going to be negative 45 degree per decade, okay? And then when you exactly hit the pole frequency, you'd be 45 degrees, Okay, you'd be 45 degrees. It should have been something like this. Okay, you'd be 45 degrees below where you started. So if you started at 90, you'd be 45 below 90. Okay, then once you hit 10 times the pole frequency, which is this guy, okay, once you hit 10 times the pole frequency, let's leave it there. Okay, once you hit 10 times the pole frequency, the pole will have dropped your phase by 90 degrees and its effect is over. Okay, pole 1 has contributed. The effect of pole 1, if you think about it, is only between 1/10 of its value to 10 times its value. That's where this phase shift is going to happen. Then beyond that or before that, pole does not have any effect. Okay, then P2 takes over. Okay, P2, which is this guy, at 10 times, at 1/10 of P2, that guy takes over and then brings about another 90 degrees of phase shift. Okay, something like that. Another 90 degrees of phase shift. This is beginning at P2 over 10. And when you measure exactly at P2, you will have dropped 45 degrees from this value. So if this value were 0 initially, you would have reached negative 45. If this was 100, you would have reached negative 55, so on and so forth. Okay, and then once you reach the 10 times the pole frequency, its effect stabilizes. Okay, so that's the idea of how phase, okay, how phase and magnitude are affected by poles and zeros. Okay, so to summarize, each at pole frequency, the magnitude begins to roll off at 45 at 20 dB per decade. Okay, and at 0 frequency, the magnitude begins to increase at 20 dB per decade. So this is going to be a negative 20 dB per decade because it's a roll off, right? So similarly, at 10 times the below the pole frequency, at P1 by 10, the phase begins to roll off at 45 degrees per decade. Okay, at P1, you have passed one decade, so phase is 45 degrees below where it started. Okay, and it continues to roll off. At P times 10, the phase stops rolling off. Okay, until then it continues to roll off at negative 45 degrees per decade. Okay, 0 does the exact opposite. And what is 0 does is at P1 over 10, 0 begins to raise at 45 degrees per decade. Okay, and when you hit pole free 0 frequency, I should have written this as Z1. When you hit the Z frequency, Z1, the phase value is a positive 45 degrees. Not positive 45 degrees, but an addition of 45 degrees to where you began. Okay, then at the Z1 times 10, your phase stops. Increase. Okay, and it will have gained 90 degrees in phase, and then it begins to flatten. So straightforward. And if you have poles lying on top of each other, or closer, or farther, or zeros closer, you can simply add these raises and fall values, and you can take the effective um, change on magnitude and phase. Okay? Questions, please. Questions so far. So that's some hint on poles and zeros. Okay? But the understanding, the assumption is that you have expressed your transfer function in this standard form. This is called the standard form. Some constant times 1 plus s over 0 by 1 plus s over t1 times 1 plus s over t2. Okay? Questions, please. Questions. Do you guys want to pick any particular example to solve? Any homework problem to solve? If you have a particular problem from the homework, I might actually have a couple of minutes to discuss that. Okay, so that's fine. So this is a quick discussion about poles and zeros. In the homework problems, you may find a pole, okay, at origin, or a zero at origin. The rules are slightly different, okay? The rules are a bit different, okay? When you're looking at a pole and zero at origin. So I want you to work on that, okay? I want you to work on that. And when you arrive, when you get to that problem, we can discuss that. But here is the idea, okay? If the textbook asks you, if the homework problem asks you to find what's the value of the magnitude, what's the magnitude in dB at f equals to 1 hertz or whatever, okay, then you don't even have to um, do the transfer function and apply a log and calculate the individual magnitudes. This is an approximation, okay? If this 20 log k naught, okay, if k naught is 1000, for example, I don't know, I'm just making numbers up. If k naught is 1000, then 20 log k naught base 10 is 20 times 3, right? 10 to the 3. K naught is 10 to the 3. Okay, for whatever reason, let's select 10 to the 4. Okay. So you will have started at 80 dB, which is 10,000. The gain is 10,000 there. In dB, it is 80. Okay. Now, using this approximation, you don't have to do the complex mathematics at all. Okay. It's going to be a very, 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 very simple arithmetic here. Okay. Let's say Z1 is at 1,000 radians per second, and P1 is at 100,000 radians per second. So that means there are 2 decades in here. 1K to 10K is a decade. 10K to 100K is another decade. So there are 2 decades. So that means it's going to raise by 40 dB, right? 20 dB per decade. So you're going to have 120 dB at this frequency, okay? Then pole 2 begins to take effect, and it counteracts the incrementing the increase of the magnitude from 0, neutralizes that to a flat value, and then begins to roll off. You get the idea, right? So between Z1 and P1, there are 2 decades, meaning that the 0 must have raised the magnitude by 40 dB, because there are 2 of those decades. Okay, so you started at 80, you go to 120. So the idea is you can do the exact same thing. If your 0 was 1000, you can plug in a value of 1000 for 0. You can plug in a value of 10,000, 100,000 for P1, and I don't know, 100 meg, 10 meg, I don't know, for a P2. Okay, you can plug in those numbers, substitute S equals to J omega, do the magnitude, 20 log all of that, or you can simply use this approximation to do this, not even on the back of the envelope, but in your mind. Okay, this approximation is going to hold good. And for the homework problems, you don't even have to calculate. You simply do the straight line approximation. Okay, I see that there are no questions, which is a good thing. So what we are going to do is to move on to the next chapter, frequency selective circuits. Okay, frequency selective circuits, high pass filters, low pass filters, band pass filters, band reject filters. Okay, so frequency selective circuits, there are 4 types: high pass, low pass, band pass, band reject. Band reject or band stop. Okay, if you have frequencies along the x-axis, and the lower frequencies are amplified or not attenuated, and the higher frequencies are killed, rolled off, attenuated, that's called a low pass filter. A low pass filter lets lower frequencies pass, but it does not let higher frequencies pass through. The best example is a home theater system, right? Where there are a subwoofer is only amplifying a select set of frequencies, low frequencies. The tweeters or the high frequency speakers are only amplifying those frequencies of interest at the higher end of the spectrum. Okay, and nothing in between or nothing below. So a low pass filter passes low frequencies and attenuates high frequencies. The name is pretty indicative. Okay, the high pass filter, what it does is it does not pass the low frequencies, but it passes the high frequencies. Okay, if this is the cutoff frequency, anything below the cutoff frequency is stopped. Okay, anything above the cutoff is passed. Okay, and then a band pass filter passes only particular bands. Okay, only this is passed, only the frequencies within this range are passed. Okay, the rest are attenuated. Okay, and then band reject filter does the exact opposite. It passes this guy and this guy, but then rejects or blocks, okay, these frequencies. Okay, those frequencies in this particular band are stopped. The rest are amplified in case of active filters. Okay. Questions, please. So 4 kinds of filters: high pass, low pass, band pass, band stop, or band reject filters. Okay, let's see. I'm not going to go through all the slides here. I will um, slowly skim through this. I'll, or rather, quickly skim through this and then stop where I want to make a point. Okay, for example, here, output over input. I think we discussed this in the previous classes as well. Output as a function of S over input as a function of S is called the transfer function. Okay. When you have a voltage over voltage, it's called a voltage gain. Okay. When you have current over current, you have a current gain. Okay. But then you can also have your output voltage and input current. Okay. So this is called a trans impedance. Okay. Then there's also trans conductance I output over V input. So if you define an output current, if you define a current to be an output and a voltage to be an input, it's called a trans conductance, so on and so forth. That's beyond the scope of this class, but what we should understand is the output voltage and the input voltage leads to a voltage gain. You're looking at a transfer function that is between two voltages. Okay, it doesn't have to be that way. Any of these voltages can be in any of these output and input can be a voltage or a current. Okay, let's see. We talked about pass band, stop band. So this is a low pass filter, right? An ideal low pass filter allows all these frequencies to pass through, and sometimes it does even amplify them in case of active filters. And in case of frequencies above that cutoff frequency, they're all stopped, okay, or attenuated. That's the idea of a low pass filter, okay. High pass filter, on the other hand, this guy attenuates or stops frequencies below the cutoff frequency, okay. This is called a brick wall filter, okay. This WC is where the cutoff is. Anything below that cutoff is stopped. Anything above that cutoff is passed. Okay, so that's a high pass filter. It has a phase response. Okay, based on the poles and zeros located there. Okay, then there is this guy, the band pass filter or a pass band filter, where anything in between the cutoff frequency lower and the cutoff frequency higher, WC1, omega cutoff 2, anything in between those frequencies is passed, and anything below or above is rejected. Okay? And there is the band reject filter that we discussed. Okay. Let's see what else. So low pass filters, you can create many different types of low pass filters. Before we go to low pass filters, I want to talk about a high pass filter, particularly one kind of high pass filter. Let's see if I have that high pass filter somewhere in here. This guy. Okay, easy way to remember. There are four kinds of circuits that you can build using R, C, R, L, using both of these. Okay, what you do is if you connect a capacitance and then place a resistance in series with it and look at the voltage across the resistance. So if you see something like this, H for a capacitance, followed by a voltage across a resistance, this is a high pass filter. Okay, I use these symbol of capacitance to hint me that it's a high pass filter. Okay, but then your analysis we should also verify that that is the case. Okay, so high pass filter is this H, okay, and the voltage taken across a resistance. Output voltage is over there, input voltage is over here. Okay, so the opposite of that is also a high pass filter when you're using an inductor. Okay, now in case of an inductor, your output voltage is V0, and that is also a high pass filter. Okay, if the capacitance was there to remind you of a H, the opposite is true for an inductor. Or you can even make the argument, so this is a high pass filter, right? Copy this. If you look at the low pass filter, okay, I'm looking for a single slide that has both. Okay, let's see, this is high pass filter. But if you were to take an inductor and a resistance, that would give you a low pass filter. Okay, an inductor voltage measured is a high pass filter. This guy is a low pass filter. Okay, you get the idea, right? If you see a capacitance and the voltage is taken across a resistance, that's H. That should remind you of a capacitance. Okay, but in general, how do you analyze any filter? Okay, in order to analyze any filter, symbolic, not just intuitively first. Okay, this is what you want to do. You want to look at extremes in frequency. Okay, the question that you should be asking yourself is, what is the V out when frequency is 0? And what is V out when frequency is extremely high, infinity? When the input frequency, when the frequency of this signal is extremely low, what is the output value? So on and so forth. Okay, so you want to look at the extremes. Okay, let's start with the frequency of the input equals to 0. Okay, an inductor acts as a short to DC. Remember, the ZL was J omega L. If the frequency omega is 0, then the impedance of this inductor is 0, meaning that it acts as a short. Okay, there's no voltage drop here. So all the voltage V in appears at V out. Okay, so if you were to look at V out over V in, then that would be perfectly 1, right? So at extremely low frequencies, you get a value of 1 for the transfer function. Okay, output over input. Let's look at the opposite. Let's see what happens when frequency, okay, when frequency is infinity. When the frequency is infinity, J omega L is infinity, meaning that this inductor acts as an open circuit. It has infinite resistance, meaning that it acts as an open circuit, right? So no current is flowing through this inductor. Therefore, the voltage dropped in this resistance is 0. So when frequency is infinity, V output is 0. So if you look at V output over V input as a transfer function, that's 0 as well. Okay, now you get the idea. If you plot frequency along the x-axis and the magnitude V output over V input along the y-axis, it would seem that you're starting at 1 and heading towards 0. Okay, that's more or less high frequencies are passed, or low frequencies are passed, and high frequencies are attenuated. Okay, that's a low pass filter, right? Low pass filter should pass all the low frequencies and it should stop the high frequencies. But it seems this guy, okay, is a very crude approximation, a very crude model that is passing low frequencies and stopping high frequencies. So you look at the gain, high frequencies have a very low gain. Does that make sense? Okay, so this is analysis, qualitative analysis of a RL circuit. Okay, let's see, the same thing is shown here. When the frequency is infinity, it acts as an open circuit. So the output voltage is 0. As a result, you see that the gain is 0 as well. That's exactly what we discussed. It starts off at 1. It begins to roll off towards 0. Okay, the phase begins at 0 and then begins to roll off towards 90 degrees. Okay. Okay, meaning that the circuit is going to become an inductive circuit. Okay, let's see. Professor Tetro also talks about half power bandwidth. Okay, which is 0.707 times the H max. Okay, at negative 3 or negative 3 dB. Okay, if you plot it in dB terms, okay, a negative 3 dB, a 3 dB roll off is considered to be half power bandwidth. Okay. Now, in terms of the voltage or current, the magnitude at the half power point is going to be 1 by square root of 2 of the maximum magnitude. Okay. So then Tetro talks about the quantitative analysis. Okay. Here is again another hint. Okay. When you are analyzing filter circuits, all you want to do is voltage division. I'm not going to go through the mathematical analysis for each of these circuits, but I will give you the single technique that you will use throughout this chapter 14. Okay, that is voltage division technique. If you're interested in finding out the V output of S, that clearly is a voltage division between R and L. Okay, so you can write the KVL or simply use the voltage division R by R plus SL. The total impedance is the sum of those two. And then the voltage drop in this guy is, so V in times this guy is equals to V out. Okay, that's exactly what we get. The output voltage is R by SL, because these two are in series, times VI. Okay, and the rest is just arranging it in order. Okay, arranging it in a format that is convenient for analysis. Okay, I'll show you another example as well. So you rearrange that, you get this format, S plus R by L R by L, so on and so forth. There are certain names, the cutoff frequency, so on and so forth. How do you get the phase out of it? Take the magnitude and the phase from this transfer function by writing it in polar form. Okay, tan inverse of imaginary part over the real part. That will give you the phase. Okay, and then real part squared plus imaginary part squared under root will give you the magnitude. Okay, so on and so forth. Go through this. I do want to give you a hint about the general approach that we will use. I'm not going to spend a lot of time doing the math. Okay, as a matter of fact, let me show this to you. Okay, equations provided. Wherever possible, you want to use these equations. Chapter 14. Okay, omega c, the cutoff frequency for a RL circuit. Okay, low pass or high pass is going to be 1 over L over R or R over L. Okay, and then if you're using an RC circuit, it's a first order circuit. Just L and R or just C and R, that gives you a first order circuit. Okay, so the cutoff frequency is going to be 1 over RC or R over L. Okay, so I encourage you to use these formulae wherever convenient. Okay, you don't have to do the analysis each time you encounter a circuit like this. Okay, so this guy, R over L, remember that was the cutoff frequency, omega c. Okay, so if you do the analysis symbolically, you'll see that this term S plus omega naught, that kind of term will give you the cutoff frequency. Let's see what else. Okay. So here is the a low pass filter again. Here is a low pass filter, right? The reason is, look at the extremes if you want. Earlier we had a low pass filter that was an inductor in series with a resistance. The resistance voltage was considered as the output. Here, you want to look at the capacitive voltage, okay, as your output. Well, if you want to look at the capacitive voltage, what do you have to do? You simply have to look at the voltage division, right? The impedance of the capacitance by impedance of the capacitance plus resistance. That's the voltage division, right? Times V input. That should give you V output, the output across the capacitance. Okay, so you can do that to do the mathematics, but let's preserve the analysis, let's preserve the intuition here and look at extremes. What happens when frequency equals to 0 and what happens when frequency equals to infinity? Okay, when frequency equals to 0, what do you think happens to this capacitor? Everybody with me? Anybody with me? When the frequency is 0, when the frequency of the input is 0, or DC, when you're applying a DC voltage, what happens to the capacitance? Does it act as a short or does it act as an open circuit? Acts as an open circuit, right? At frequency, cap is open circuit, meaning that there is no current flowing in this. and the voltage drop across the resistance is 0. So all the voltage from the input appears here. Okay, that's a voltage drop. So V output equals to V in on one extreme. Okay, and on the other extreme, when your frequency is infinity, okay, this capacitance acts as a short, meaning that the output voltage, there's no voltage drop across a short. Okay, so capacitance is a short circuit. Okay, therefore V output equals to 0. Okay, so the idea is if you were to plot V output over V input, at low frequencies it's going to be 1, because at low frequencies its value is 1 and it goes towards 0, hence a low pass filter. Okay, let me show that to you. Okay, so it begins at 1. Okay, 20 log of 1 is, when you write it in dB format, 20 log of 1. Okay, then it's going to be 0, right? So begins at 1, okay, and falls towards 0. Okay, that's the idea. That's the idea of a low pass filter. Okay, an ideal low pass filter should have this kind of response, right? Pass, stop. But this guy, the real first order filter, passes that frequencies and attenuates these frequencies. Okay, so that's a low pass filter. The opposite is true for a high pass filter. Okay, if you were to go to the
Professor,
yes.
I had a quick question actually. So for the inductor, you showed the impedance, how when the omega is 0 and then omega is infinity,
Yeah.
the mathematical representation. But for a capacitor, isn't it? I mean, I just don't get the math behind it. Isn't it 1 over omega? So when you have 0 impedance, well, I mean, when omega is 0, don't you have 1 over 0?
Yeah, that's right. That's
Yeah.
right. 1 over 0 is what?
The open circuit? Okay.
Does that answer your question?
Yeah, that answers the question.
Okay. Okay. So he has an excellent question. At DC voltages, right? At DC voltages, when the input voltage is 0, I mentioned this is an open circuit, right? Why is it an open circuit? That's a good question, because this capacitance ZC is 1 over S times C, or 1 over J omega C. When omega is 0, all of these things, ZC turns out to be 1 over 0, which is infinity. That's exactly what an open circuit is, right? So capacitance acts as an open circuit to DC. That's a good question. Okay. Other questions, please. Okay. Good. Thank you. So now capacitance. So these are rules of thumb, right? Cap acts as a short to high frequencies, acts as an open circuit to low frequencies. The exact opposite for an inductor. Inductor acts as a short to low frequencies, acts as an open circuit for frequencies that are extremely high. Okay. So here you do the voltage division again. Okay, you're interested in finding out V naught or V0. V0 is a voltage division between the capacitance and the resistance. Okay. You should not be thrown off. Okay, there's some definitions. Tau, RC is called the time constant. 1 over RC will give you the cutoff frequency, so on and so forth. Okay, so the same thing here for a high pass filter. If you want to write the transfer function of a high pass filter here, that would be R by R plus ZC times V input should give you V output. So if you want to write the transfer function, you bring V input to this side. That's the definition of a transfer function, right? Output over input. The same thing here. V output over V input is ZL by ZL plus R. So the output here, that's the voltage division, right? So you plug in the expression for ZL and ZC, okay? Somewhere in here. ZL. So this is ZL by ZL plus R. That's the voltage division, right? So let's go back. ZL by ZL plus R. That's all there is to it, okay? And then, of course, you do the magnitude and phase response. But here is the classic. If you see this, it's a low-pass filter. If you see this, it's a high-pass filter. Okay? Etch it in your mind. A low-pass filter passes low frequencies and has a low gain to high frequencies. Okay? High-pass filter has a low gain to low frequencies, but a big enough gain to high frequencies. Okay? What is a high and what is a low frequency is defined by this cutoff. Anything to the left is a high frequency, is a low frequency. Anything to the right is a high frequency. Okay, let's see what else. Let's see if we should go to the idea of band pass filters and band reject filters. So there's an idea of loading, of course. Okay, there's an idea of loading. How do you calculate the transfer function when there is not just a resistance and an inductor, but another resistance in parallel? Well, that's pretty straightforward. We still do the voltage division between this guy and this guy. Okay, so L in parallel with RL is the effective resistance of this guy that is in series with R. So the voltage division is going to be this parallel combination Z parallel by R plus Z parallel. That's still a voltage division, right? So that's called loading. Loading has an effect of reducing your gain and also reducing your cutoff frequency, okay? You will find out from Tetro's videos, okay? So the gain or the magnitude, output magnitude is reduced for a loaded circuit. Whereas without the parallel, if you did not have this resistance, then that would be unloaded. But with the resistance, if you have that RL load resistance, you're going to have a lower magnitude, lower value for the magnitude. Okay. Let's see. So that's about high pass and low pass filters. Okay. Then there is the band pass filter, which stops everything to the left of W1 and everything to the right of WC2. Okay. If the frequency is less than WC1, then the gain or the magnitude of the transfer function would be 0. Whereas if frequency was omega C2, then the gain would still be 0. The gain or the output over input value transfer function would be 0. Okay, but in between these two values, if the frequency lies in between omega C1 and omega C2, then you have the transfer function value that is not zero. Okay, so that's the idea of a band pass filter. And this frequency omega naught, okay, omega naught is defined as the center frequency. That's simply the geometric mean of omega C1 and omega C2. Okay, what else? So there are certain definitions that you still have to remember, something like this. Okay, these definitions and all, most of these, don't try to redo the math wherever not necessary. Simply plug in these values wherever you can. For example, beta is defined as the bandwidth, is the difference between the upper cutoff frequency and the lower cutoff frequency. Okay, Q, the quality factor, is simply the omega C1, omega C2 square root divided by omega C2 minus omega C1. It's a quality factor. Okay, so don't do the math wherever you don't have to. Don't do the analysis if you don't have to. Okay, it's a good idea to do that once or twice, just so you understand the arithmetic equations that underlie the theory that underlies these formulas. Okay, so when you're interested in the RLC circuit here, for example, RLC circuit can act as a bandpass filter. Okay, then your output V out would still be R over R plus ZC plus ZL, right? That's the voltage division again. Okay, and you have to plug in 1 over SC for ZC, SL in place of inductor, and then do the voltage division. Okay, look at the extremes if you wanted to. Okay, what happens when the frequency is zero? All the voltage appears at the output. Okay, so on and so forth. So this is a band stop filter. Okay, okay. So look at the extremes and you'll find out what's going on. Okay. Now let's see. So that's about. So these terms are defined. What's the value for omega naught? Well, 1 over LC. So this is called a second order filter, because if you do the math here for the series RLC circuit, you'll see that the denominator is actually a polynomial in the second order, second degree for S. Okay, so it's a second order filter, and then it has a very specific transfer function. Go through that. Okay, so pay attention to the definition of bandwidth, which is omega C2 minus omega C1. Okay, what else? Okay, so go through Tetro's videos that talk about the band pass, band reject filters, so on and so forth. Okay, there are a bunch of different um, series RLC circuit. If you're taking the voltage across the L and C, that will be a band reject filter. Okay, that will be a band reject filter. But if you're taking the voltage across the resistance, that will be a band pass filter. Okay. What I want to do is to give you some time to go through the videos and work on some problems. Okay, that way, when you come back, you can ask me some questions if you're uncomfortable about a particular um, open circuit, right? Okay, if you're uncomfortable about a particular problem, you can bring back those problems. So in tomorrow's class, I will talk a little bit about these band pass, band reject filters, but I expect that you will have gone through these videos, worked on some homework problems. It could be band pass, band reject, or whatever, or it could even be the Bode plots. Okay, whichever ones. So work on these homeworks, work on these um, frequency selective circuit problems, and then tomorrow we'll go over um, some of the similar concepts, related concepts, and hopefully devote a lot of class time to working problems that you had problem with. Okay, if you had a problem with a particular problem, bring that to the class. Okay, so that's a good place to start, unless you have questions.